Hello everyone. So today we have Megan Kerr presenting her research on Antarctica. So Megan is a first-year PhD student at UTIG, advised by Duncan Young. She graduated from Missouri University of Science and Technology in 2021 with a bachelor's degree in geological engineering. While at Missouri S&P, she was actively involved in the school's Mars rover design team and completed some internships with Rio Tinto and the Missouri Geological Survey. Her undergraduate research explored the impact of fault roughness and pore pressure on seismicity in Oklahoma. She's excited to continue her education here at UT, where she's investigating the relationship between subglacial geology and ice sheet dynamics in Antarctica. So take it away, very excited.
Can you move the thing? Okay, wonderful. So hello everyone. As Duncan said, I'm going to be talking about my fieldwork in Antarctica. And most of what this talk is going to be is like the motivation for what I'm planning to do with my PhD, given that we just did the field work. So the data is kind of young, but let's get into it. So, right, quick overview of the season. So this was the first of two planned airborne surveys that we're going to be doing near the South Pole for Coldex, which I'll explain in the next slide. But we collected over 20,000 line kilometers of new airborne geophysical data. These images that you'll see, the one on the left, your left, is a field team in front of the plane that we used to survey. And then we have just an overview of the flight lines that we collected. So here's the team. They're wonderful. We have Duncan, who is my advisor here at UT. Gonzo was he's like a contract worker, I guess, with UT. He does like he was just very important for getting the instruments on and off the plane, doing logistics at McMurdo. Dylan is right there. He's an engineer. Christian is a grad student here at UT. There's me. And then John Payton is co-PI of the project with Duncan at the Center for Remote Sensing and Integrated Systems. And then Shravan is his PhD student. And we have Jamin, who was a student here and who is now a research scientist at Scripps. So I mentioned Coldex earlier. What is Coldex? Is the Center for Oldest Ice Exploration. You guys can read. But essentially, it's this huge NSF-funded science and technology center made up of a bunch of different institutions with the goal, two goals, lots of goals, but of basically finding old ice. And so for the first 5 years of the project, there are two main objectives. Two main science objectives, at least, because diversity and education are important too. The first one is finding really old discontinuous ice, so like over 2.5 million years old, along the margins of the ice sheet in Antarctica. And then the second is finding less old, but still really old ice, about 1.5 million years old in the interior. And that is the one we're going to focus on because that's the one UTIG is involved in. So why 1.5 million year old ice? Well, why ice first? This is a beautiful picture. It was not taken by me, it was taken by Peter Neff. And this is an ice core. You can see all of the air bubbles. And basically those air bubbles are like the best data we have for like past climate and atmospheric reconstructions. But also you can get temperature, snow accumulation, all of these important things to reconstruct the climate using ice, and just like the accuracy and precision is just very high. Ice is great. But why 1.5 million years? So a lot of interesting climate things have happened that I don't understand over the past couple million years. a few million years, I guess. So the climate used to be warmer, it's gotten cooler, getting warmer again, as we all know. Continental glaciation started and intensified, and then also what we're like really interested in is this thing called the mid-Pleistocene transition, during which the glacial cycle shifted from happening basically every 40,000 years to every 100,000 years. And we're not really sure why that happened, or what exactly the climate was like before that, like in the 40K world versus our current 100K world. So the thing is that our continuous ice core record extends to right after the mid-Pleistocene transition. The blue line is the continuous ice core record. Those light blue squares are the discontinuous record. So basically there is really, really old ice, like older than the continuous record, but it's along the margins and it's not like continuous. So you only get like one snapshot at one point in time, which is also really important. But for these purposes, we're interested in getting a continuous ice core record through the mid-Pleistocene transition and into the 40K world. So this is a really big international effort. Lots of countries have teams in Antarctica looking for old ice or currently drilling for old ice. And you'll notice that all of these countries are pretty much focused in in the interior of East Antarctica. And that's true for a lot of reasons. But there are basically like these accepted conditions that we believe are good, necessary for the preservation of like really old ice. And so you have things like low accumulation rates, being close to like the ice divides. So where there's really low ice velocity, the bedrock is smooth, the ice thickness is around like 2,500 meters, and there's low geothermal heat flow. And these are all like really important, sometimes hard to quantify. They interact with each other in like annoying ways. And what's my next slide? Right, okay, sorry. So there are a lot of ways to characterize the ice sheet and what's going on beneath the ice sheet, and finding old ice. And so ice penetrating radar is kind of like one of our best tools for doing that. Like you can see these we make these beautiful radargrams where you can see the surface of the ice really clearly, layers like englacial layers, and then also the bedrock. And so this is a radargram from our survey. It's the red line. I don't know if you guys can see it very well, but it's pretty cool. You can see like there are parts of the bedrock that are shinier than others. There's this like weird area where it's like flat. I don't know what's going on there yet, but it's cool, right? But you'll notice that there's this area at the bottom of the ice sheet you can't see the layers, but it's not bedrock. But if you think about it, the ice at the bottom of the ice sheet is going to be the oldest ice, right? That's the stuff we want. But if it's there are a lot of theories as to what's going on down there. So is it like an instrumentation problem? Is like the ice just really deformed? Has it like melted and like refrozen? Is it like a layer of like stagnant ice? We're not sure. It can be different things in different places. And it's obviously difficult to know what's going on down there just with radar. And also, you know, if you have like very deformed or like ice or like weird like flow dynamics going on down there, that's bad for the paleoclimate record, right? So we need other ways to basically figure out what's going on at the bottom of the ice sheet, and like whether or not the ice is valuable to us. So that's what I'm going to be doing. Duncan likes to call it the bottom-up approach. basically looking at the basal layer from and how it's impacted by like subglacial geology, hydrology, geothermal heat flow, all of these things that interact and can do annoying things to the ice. So that's what I'm going to be talking about. But specifically in this talk, I'm going to be talking about geothermal heat flow, why is it important for old ice preservation? How is it characterized? And where does our survey that we just did and that we'll be doing fit in? Also, I took this picture. Nice. It's so good. Oh, sorry, I'll explain. This is at Williams Field in McMurdo, and the thing in the background is Mount Erebus, which is a volcano. Whoa. Okay, so science though. Why is geothermal heat flow important for old ice preservation? This study by Lubes and others in 2006, basically they wanted to see how different areas of Antarctica, like how sensitive they were to increases in geothermal heat flow. So they modeled an Antarctica with geothermal heat flow of 40 milliwatt per meter squared and an Antarctica with 60. And they found overall, there were increases in basal melt rates, increases in the area of the ice sheet that was of the bottom of the ice sheet that was like at the pressure melting point, increased just melting in general, which is understandable because if you heat ice up, it's going to heat up. But the interesting thing that they found was the difference between the two was greater in the interior of the ice sheet. So you see where the red is. That's a greater difference between the two. And if you'll remember, that's basically exactly where we're looking for old ice. So that just means that the area that we're looking is more sensitive to changes in geothermal heat flow. Why is that? Well, basically energy at the bottom of the ice sheet is conserved. And so a lot of there are all these contributions to the heat at the bottom of the ice sheet. So you have geothermal heat flow, the friction from the ice sheet sliding, water, etc. And then if you think about the differences between ice in the interior and ice in the exterior, ice in the interior, for one, it's flowing a lot slower. It's flowing so slowly that the heat generated by friction is basically negligible, which is really important because when the ice is flowing quickly, then that contribution is like orders of magnitude bigger than the contribution for geothermal heat flow. So getting rid of that just makes the contribution of geothermal heat flow even like much bigger. But also the ice is thicker. So there's higher pressure at the bottom of the ice sheet, which means that the ice down there is where the temperature is closer to the pressure melting point of water. So the contribution of heat required to maintain water pressure melting point is also lower. And finally, ice is a great insulator. So you're insulating the base of the ice sheet from the surface, which is colder. So that contribution is also smaller. Another study looked at the effect of spatial variability in geothermal heat flow in an area of East Antarctica, and they found that, so the study basically, they modeled 500 spatially variable fields of geothermal heat flow in an area, and then also a not variable field that had the same, that was the same as the background mean for all of those. And in every single situation, the spatially variable fields predicted higher melt rates and higher basal temperatures than the completely flat field. And they also found that the fields with the low pass filter cutoffs of about 100 kilometers predicted the lowest melt rates. And that's kind of an issue because many popular geothermal heat flow estimates have resolutions of about 100 to 200 kilometers. So they're likely underestimating the impact of heat flow on melt. Additionally, we know that there is small scale variability near the South Pole. There is a study by Jordan and others found that there's an area of likely melt near South Pole that is like 60 kilometers away from an area of likely frozen bed. So essentially, geothermal heat flow can change and affect basal conditions at small scales near the area that we're looking. So to sum up that little section, small variations in heat flow can strongly influence basal thermal conditions, especially in regions that we're looking. Heat flow can change at scales not captured by most current models, and essentially we need higher resolution estimates to get an accurate idea of what's going on down there. So how do we know? Like, how do we characterize geothermal heat flow? It's really hard to measure like directly. There is an ice sheet that exists. And so basically we have to measure or model or estimate the things that impact geothermal heat flow. And those are heat production, tectonic history, thickness of the crust and mantle, composition of the crust and mantle, and age. And to illustrate just how much some of these impact heat flow, we have this diagram on the right is showing crustal thickness in Antarctica. Blue is thick crust, and red is, or orange is thin crust. So East Antarctica, West Antarctica. And then if you look at this is the mean of all those estimates, the studies that I showed earlier. Red is high geothermal heat flow and blue is low geothermal heat flow. And they do sort of line up, don't they? So how do we measure these things? It's all very indirect, but so one way is we use gravity anomalies. We essentially we observe the change in gravity over a certain area, and they do a bunch of corrections to get rid of the effect of like airplane acceleration and like distance from the ground and the effect of topography. So we basically strip away everything except for what's happening at like the deeper levels. And we can figure out the depth to the mantle lithosphere boundary and put that into models of the mantle and lithosphere, and then a bunch of assumptions, and then that can give us an idea of what the surface heat flow is. We also have magnetics, which is sort of similar, but we get the magnetic anomaly and we can do a bunch of stuff to that and then figure out at what point basically metals get demagnetized or minerals get demagnetized. And once we know like that depth at like areas, we can put that into models and then, more estimates of surface heat flow. Finally, we have radar, which can tell us, we can use like elevation, specularity, reflectivity, like the actual englacial layer configuration to figure out where there could be subglacial water, where there may have been water in the past, and use that as a constraint on heat flow, and then get more estimates on heat flow. And so all of these together can give us a really good idea of what's going on. And then we can use that to figure out where there might be old ice. So I'm going through this a lot faster than I thought I would, I'll be honest. But so let's look at some data that we got. And again, I want to reiterate that we got this data like 2 months ago. It is a baby. It is baby data. That's
So
just.
what are you saying? Babies are still ugly?
Yes, Eric. All right. All right. So first of all, before we look at the data, how did we get the data? So we flew this plane. It's called a Basler, and it is a basically it used to be a different plane, and then it got like outfitted. This plane flew in D-Day. What? That's wild. Yeah, no, so it was super great. A bunch of like the airline that like flies it, they're Canadians, which I don't know why I mentioned that, but they're from Canada. Anyway, so what kind of instruments were on this plane? So we had, and I'm just gonna talk about the UTIG stuff. There's a bunch of KU things that I'm not going to talk about. It's not entirely relevant, and I also am incapable. But so we have Marfa dual channel radar sounder that operates at about 60 megahertz, and we have one of those on each wing. And then we also have a gravimeter that Gonzo and Jamin are like really happy about, apparently, on the plane. They're fixing it, yeah. And then we also on the back, this like weird tail thing. This is the where the magnetometer is housed. Not shown. We have a bunch of GPS receivers on the wings, the tail, and the center of gravity. The gravimeter is also at the center of gravity of the plane. And then laser altimeter and a camera looking down through a window in the floor of the plane, which you obviously can't see. So that is how we retrieve the data. We're going to be talking about this radar line called CLX MKB2N X58B, which really rolls off the tongue. And it's right here. To orient. So this is South Pole. This is where all the lines are coming out of. And that was where we operate out of the South Pole station. And then over this way is Dome A, which is basically the highest point on the Antarctic ice sheet. It's maybe where glaciation started at some point. I don't know much about it, but it's important. So we're basically on like the flank of the dome. And then, so if we look at this radargram, it's a really good radargram. You can see the surface really easily, the layers are beautiful, and the bedrock topography is like super cool. It's interesting. It's probably bad.
Resolution of the bedrock topography, sorry.
What was that?
The resolution of the bedrock topography. That sharp fluctuations, that's trying to get my hand around the resolution of this.
So from like this radar line is about like 200 kilometers long.
Yeah, but
so
those sharp fluctuations, what you're talking about, 50 meters scale fluctuation, 200?
I am not entirely sure.
Few tens.
Few tens. All right, thanks, Don. But anyway, also someplace like this, bad for old ice. Because of like how much the bedrock is fluctuating. If you think about it's gonna deform the ice as it moves. So that's bad. But anyway, moving on. So here are some maps of so we have bed elevation right here, and then surface elevation, and I like plotted those as a profile. And it looks just like the radargram. It's not surprising. It's good that Python works. So next, we have ice thickness, which again, Python works. It makes a lot of sense that the ice thickness would just be an inverse of the bed elevation. So again, not super interesting, but good. This is a little bit more interesting. We have the free air gravity anomaly, which we can see it sort of, so lines up with the topography. The thing about gravity is that you, so this isn't corrected for the topography. And once we take that out, then a lot of like the smaller scale, high frequency fluctuations will go away, because higher frequent, like the shallower the like feature, the higher frequency, what's the word, anomaly you'll get. So still have some work to do on this to actually see what's going on in the deeper layers that we're interested in. And finally, we have magnetic anomaly. And I know it looks really interesting, but don't be fooled, because this has not been corrected for like space weather. So essentially, we don't know if like these like big bumps are due to like an actual magnetic like anomaly, or if it's just due to like the sun was acting up that day. So again, like don't, but it's cool, right? It looks cool. I told you this is baby data. Future work, this slide is not done, I don't think. But it's a fun picture. There's this hike at McMurdo, and this is like right at the beginning of the hike. Someone was like, anyway, it doesn't matter. Future work is basically everything that I just told you about. Also, we're going back to Antarctica in November to do like so this survey was like reconnaissance, like very like high level. We're gonna basically go and choose like smaller areas that we can do like denser grids on to get a better idea. So we need to figure out the plan for that. And we'll go back and then we'll do the whole thing over again, and it'll be wonderful. So summary, I don't have to say all of this again, but essentially geothermal heat flow, very important for figuring out where old ice is or isn't. And that is my goal for probably the next few years. So fun. Would like to thank South Pole Station, Boric, Codex, NSF, funding from Bedelson, and then Scott and Greg, who have been helping with processing the data and getting the data. Also, this is me at the South Pole Gravity Station. As you can see, these are in the ice tunnels underneath like the station. It's like -60 down there. I was really cold. And then I looked a lot like Ralphie from A Christmas Story. So, that's my talk. Does anyone have any questions? I don't know who's first. Fight.
Did you take that picture?
I did. Yeah.
I have an actual question. So you were talking about finding the signature of paleo melting. What is that? And is it in the ice? And you then have to like track the ice backwards as it moves?
So this is something that I actually don't know a whole lot about, but if we like look at like, so if you like look at the layers, this isn't a very good this isn't like super interesting, but essentially like sometimes you can have like layers being cut off or layers like being drawn down that isn't like all of these layers. You can see that they kind of just correspond to topography, but if there's something interesting happening that like isn't corresponding to topography, then you're like, oh well, something could have happened in the past that like affected whether ice was like what's the word, like eroded, or if it like just didn't like if it was melted or stuff like that. So I think that's my best understanding of it.
And then if you wanted to like relate it to, I don't know, there's some random spot of high geothermal energy that melted it, would you do that, or is that too many steps of interpretation?
I do not know. Aaron?
Two questions. One really important one. Did you get to see any penguins while you were there?
Everyone asked that. Yes, I did. But like barely. It was one of my last days in McMurdo on the way back. And they were like really far away on the ice sheet, and someone set up a telescope in like the science building to like just at the penguins. And so I was at a bar, and then someone told, I think Dylan told me about the penguins or something. And then I ran to Prairie and I looked at the penguins. I was like, those are penguins.
Second, I'm not very familiar with East Antarctica, but have there been any previous magnetic surveys that you guys can like compare your more high res ones to?
Yeah, there have been quite a few. I should have included them in like backup slides, but this like the specific area that we are over, it intersects with like a few other surveys, like the AGAP surveys and like polar gap. But it's not so we can like tie our data to that. But yeah, the answer is yes.
Yeah, believe it or not, South Pole's the hardest place to work out of, because so many people want to be there. It's actually easier to do the rest of East Antarctica. So we've essentially done all the rest of East Antarctica, and South Pole's the last one. Because it's politically most difficult to get into.
It is also kind of annoying because a lot of satellites that would get data from like they just don't go over the pole, which is just quite annoying. So
yeah, so I'm also not very familiar with East Antarctica, but are the variations in the geothermal heat flow enough to change how the ice sheets flow over the bedrock? Or is this two-part inland that there really isn't that much appreciable flow of the ice sheet?
So I know that like, so if you like apply heat to ice, it's like the way it like behaves is going to be different, right? Like it's going to become like more viscous. So it might actually I think it does. Like they're like I think they've like it might impact like channelized flow in East Antarctica and elsewhere. But don't quote me on that. And then I can't give you like a good answer. I think I'm just gonna say probably. I don't know.
Yeah, it does.
You know?
But it makes a difference whether there's sedimentary rock in contact with the ice and crystalline rock.
Okay.
You know, just think about it, because the water organizes itself differently over the sediments. And so when you take those two things and put them together, you know, the heat flow involved with the rock type,
Okay, yeah.
then it makes a big difference. And then water collects some places and it stays away from other places, you know, and it doesn't, that's why it's important for old ice. You know, if you can find a place where the water isn't, then the ice gets to stay. And if the ice stays here for a few million years.
All right. Thank you.
And
Yeah, so this is really cool. There was a question about it as well.
okay.
So this is like quite rough. So would that have like more frictional heating, or is that just not important because it like is moving so slowly?
So I'm not, I mean, like I would have to assume, right, that there would be more like friction. I think the bigger issue is that like if you have like a sheet of ice that's going over like a very flat surface, the ice at the bottom isn't going to get like jumbled up and deformed. But if you have ice that's going over like spikes, like rock spikes, you know, that's gonna like mess things up a little bit at the bottom. And then that would like impact the like quality of like your ice core, right?
Yeah, makes sense.
So
Thanks.
Michaela.
Really awesome talk. Like really, pictures are amazing. So I have 3 questions. Sorry. They're all fun, I promise. They're all fun. So 1, how many surveys do you have to do until you're like, okay, this is the place to drill for the oldest ice, or have they already picked out a spot for the oldest ice?
So I told you, like, this is like a really big effort with like a lot of different institutions. So basically the data that we're collecting is going to go into models that ice sheet modelers are modeling. And we are not those people. So I don't know, we still, okay, so Poldex, so we have like this airborne survey, and we've got another one next year, and then after that there are planned ground surveys like that at even higher resolution. And then after that they have they want to do like rapid access drilling to basically make sure that places are good, and then after that they're gonna say, okay, we're gonna set up an actual like deep core operation. So it's gonna be a while.
Okay, darn.
Yeah,
Maybe at the end of your PhD.
maybe I hope I'm gone by then.
Oh. Okay.
Not gone from the project. I mean, done with my PhD.
My second one was, do you know which ice sheet models are currently being implemented? Okay, my third question. So you mentioned earlier that you want to find like a relatively like flat place instead of like the really bumpy parts, because that's where all the deformation is happening. So like how, to what extent, like over hundreds of kilometers, is like 10 kilometers good enough, or is that just like such a small area for people to like having certainty like that it's going to be there, you know? Like how big does this area need to be?
That's a good question. I don't know.
Okay, cool.
Duncan?
So the modeling team that's in Coldex is the University of Washington with where they're modeling. Michelle got that, is leading that up. And then the area, and so there's been another old ice drilling effort the Europeans led that we got support. And they're drilling on little patches which are a couple of kilometers wide of flat terrain, which involve subglacial lakes right next to them. It's a very rough area in a place called Dome Sea. This area looks to have a different character. Megan's been hunting through the data. It hasn't really seen much in the way of lakes. It doesn't seem to be the kind of this flat and valley topography that we sort of don't see. It's a little bit more spiky, but we haven't focused this data yet. So the final resolution is going to be on the order of 10 meters or so. But right now it's on the kilometers because we haven't focusing.
For the radar run.
For the radar run, yeah. So yeah, we're still getting a handle on what it means to be flat enough. We do have some variation here. There's a big area by South Pole, which is really flat here. But that's close to this area where there's this melting, and also where there's been flow reorganization over time.
Because I imagine like it's gotta also be flat upstream, right? Is it upstream, right? Because if the ice is flowed over a rough area and then goes to a flat area, it keeps that deformation, I imagine. It's more of a comment than question, but
that's where you get into the mysteries of that base of the area.
okay.
I think I saw Eric first.
So one is a comment that you guys should think about. I saw that you use geometrics, and I don't know, probably it's not compensated the data yet, and not no reduction to fall. It's really hard to compensate a MEG, and I know it from the AUV word, and I have experience with geometrics. It's not the best. So think about it when you're processing. Second, the thickness, if I see like I take it to 200 kilometers, so the black layer above the basement, the high reflector basement, should be what, 2 to 5 kilometers, roughly. Just estimating, that's what I'm saying. Now you don't see anything. What is it over there on the radar? But you're taking gravity and magnetic, which are low resolution, higher scales methods, and you're trying to know what's going on in the bottom. How do you kind of tends to address that with low resolution method. The radar is a high resolution method, although it doesn't really tells you what's that black stripe above the basement.
You mean in the ice?
Yeah, in the ice. Yeah,
Yeah.
you know, it's water, it's
The reason it's, the number one reason it's dark is that the attenuation of radar through ice is hugely non-linearly temperature dependent.
okay.
And so as you get towards the pressure melting point at the bottom, then the energy just gets sucked out. So basically, something has to be really, really, really in big contrast down deep to show up the same way it does.
Okay.
Shallow in the ice. So you're looking primarily at the temperature contrast. But the weird thing is that the rheology, it's really soft at the bottom as well. And so then everything that's flat above it gets sloped below it. And so you got geometry and losses. It's really, really hard. And then it just gets really weird. There's overturning. It's a metamorphic geology problem as you get to the bottom. And that's shown up in the blue ice that they're drilling, because those are just isolated pieces that get excavated from the bottom behind the Transantarctic Mountains, and they're all turned over. So finding old ice, you know, everyone wants to find it as a sedimentary rock. You notice those two bullets for Coldex. One is find it as a sedimentary rock where the time series is continuous. And the other one is find pieces, you know, that you can date chemically and prove how old it is. And so I think Coldex is going to have to do both. And this area is really messed up. And so that's the challenge. That's the bottoms of that's Megan. She's got to figure it out, you know.
So what's what's the estimation of all dice like you? I'm just thinking about like.
So there's a resolution
Yeah.
requirement, but basically you want to be able to sample about 20,000 years per meter in the ice. So that kind of sets constraint on how, you know, the age density that we're after in order to trace these 40,000 years cycles.
It'll all be packed in the bottom few hundred meters,
Yeah.
which is the dark spot.
Yeah, that's what I'm concerned at, because magnetic and gravity are not for that kind of like dark spot small, but when you integrate everything, I guess you'll get an answer.
Yeah, Schwei's doing that right now because we have a whole nother survey in East Antarctica where we're looking at a lake evolution in canyons, you know, and basically what's really nice is that, you know, the magnetics gives you a structural overlay. Because you can locate the position of fault quite accurately. It's really difficult to do much, you know, either side, but basically the position. And so you can tell what topography is structurally controlled, you know, and then you have to come in with the gravity and just keep turning it into a bigger and bigger piece until you get a number you can believe for the density. So to decide whether it's a sedimentary rock or a crystalline rock. So you can do it. It's sort of an art form, you know, getting out of the geology. But Schwei was able to basically use the magnetics to get reasonably thin sedimentary layers over fault controlled terrain. So you can do some amazing stuff if the magnetics, you know, if the magnetics is friendly.
And one sheet we have in Antarctica, the field lines is pretty much vertical. So
A
little bit simpler. Plus the fact we're about a few kilometers.
That's
away.
true, yeah, that helps you, but still in that topography, I just know it from hydrothermal events, for instance, from TED. The magnetic was always shifted by a kilometer from the electrical data. And it's because it's really hard to zoom in on the magnetic data on there.
We have lots of remnant magnetization here too, which is crazy.
Yeah.
Because all of a sudden you get a pole points over that way. And you realize that it has absolutely nothing to do with you know, the current magnetic field.
Well, it's great that you said she can have 20,000 kilometers of data.
So Sophia, any question?
So I don't know anything about ice. But what kind of resolution can you get with a core of ice or like in the spots that you're looking at, you know?
Like, well, Duncan just said like 20,000 years per meter.
Oh, okay.
Is the target?
Is the target.
It's basically that's how old the ice is in the context of that ice core
Okay.
with respect to how
Right.
rapidly it's thinning. But the methods right now, about a meter that they are experimenting with continuous flow techniques,
Okay.
where they're just melting off the end as opposed to grabbing a chunk.
A lot of that work is being done at Oregon State,
Okay.
those people.
And then I think you said this on one of your first slides, but the oldest ice, like 2 to 4 million years, is on the outsides.
Mhm.
Okay, that seems kind of counterintuitive. to me.
Right, well,
Why?
So
Why is it like?
basically, like there are areas where like the ice sheet goes up against like these topographic like highs and it gets like kind of overturned. So it just brings the ice at the bottom, like the blue ice at the bottom, up like closer to the top.
Okay.
And the place that our very oldest ice, it's at like it's called the Allen Hills. It's near McMurdo along the coast.
Why does that?
I think Schweiz has handled for a while.
Just to follow.
Oh, okay, I go ahead.
Just to follow on it, it's just chunks of old.
Mhm.
So why are they older than like the deepest ice? I mean, they get kind of just held up as the sheet, I guess, and the rest of the ice sheet just goes past them. Why are they so old?
You mean
5 million years?
the blue ice areas?
Yeah, I can understand it seems to be turned over, but.
That means that old ice is all over the place underneath the ice sheet. And
It
the
is.
only place it gets excavated and brought up to the surface is at the edges, at the mountains.
So it's not older necessarily than the basal ice.
It's not necessarily older out there, it's just basically more available. It's on, that's where the streetlight's on, you know, the old ice comes up to the surface and it's blue. Because the only reason it comes up to the surface is because the snow doesn't pile up on top of it. It all gets blown off, and so it's basically being eroded at the surface by the atmosphere.
Right, Troy?
Yeah, two questions. First one, why South Pole? It's a huge commitment of time and money and personnel to do this kind of survey. And Don mentioned there was no data in that area. So what hint do you guys have before you go out there and invest all the time and effort?
I think one of the biggest things is that there is a US run research station at the South Pole. I think that's one of the big ones. Like it's just Antarctica is a very difficult place to do field work. And having, you know, like a research station, being able to be like near that and like fly out of it is just it makes things a lot easier. And I assume less expensive than like a field camp. But anyway, and then also just let's see, I mean, the South Pole, it's in East Antarctica, it fulfills or is thought to fulfill a lot of these like accumulation rates like very low. Dome A is like over here. Oops. Like this, yeah, Dome A right here. So that's like the coldest, like driest place, basically. Yeah, it just it just makes a lot of sense. It's where the yeah.
And the second one is more of like a discussion. So basically, my understanding is that you're going to use gravity and magnetic as help of radar to constrain where is the best site for potential old ice preservation. Now, describe what that site would look like on your gravity curve or magnetic curve. If that's
Fine to say no. Just wonder, just curious.
I was talking to Shwai earlier and I was like, ask me easy questions. Oh my God. Yeah, I don't know.
It's fine.
I'm not gonna attempt that right now.
It's good. Amazing.
Thanks, Shwai. Any other questions? Awesome.
I have a question, sorry.
Oh.
Can you,
Go
okay, you
ahead,
can hear me.
Ben.
I really enjoyed that presentation, thank you, that was great. And it just sounds like really exciting work. I'm so glad y'all got to go down there finally. I know it was quite ordeal. I was wondering, like, so these things that you listed, these conditions necessary for old ice preservation, you know, you are testing these hypotheses about this climate transition that happened 800,000 years ago. So I guess you kind of have to think about not only areas where these things are true today, but also areas where they've been true for like the last 800,000 years. And I was just wondering, do you think that any of these have like changed on the timescale of interest for your location? Or are you pretty confident that that this area has been ideal for this purpose kind of since the mid-Pleistocene transition? Do you have any thoughts about that?
Well, I think so. I think I do have thoughts. So we've been through like a few glacial cycles, since, you know, 1.5 million years ago. So I guess I would assume that at least where it has to do with like the ice itself and like the extent of the ice and like accumulation and whatnot, then that's likely changed back and forth a few times. When it comes to like the actual geology, I'm sure that's less variable temporally. But geology is weird, right? So I don't really know.
Totally. Okay, cool. Thank you.
Yeah, thanks. We good?
Hey, yeah, I guess we can thank Megan once again for a really great talk. And see everyone next week.
Thank you guys.